Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jia-Yu with us today. Hi, Jia-Yu.
Hi,
Where are you located? Jia-Yu?
I now is a PhD student in the National Central University in Taiwan.
Excellent. Very good. Very good. Is it springtime in Taiwan? Are there blossoms or is summer? Has summer already arrived?
Yeah. It's about maybe 25 degrees.
Okay. Okay. Nice and toasty. Very good. Jia-Yu, what do you like to do for research?
Yeah, actually, interested in the macro variable, long periodic variable, and
Okay.
also I like with the machine learning technology too,
Okay.
and some Python languages or something.
Okay. I'm with you. Very cool. And that is going to bring us to this very nice AJ article. As soon as I get it up. This very lovely AJ article. It's open access, people. You can go get it for free. Go grab it. The difference of photometric properties between regular and non-regular Miras in the Magellanic clouds. And Jia-Yu, take us away.
Yeah, okay. So just I mentioned, I'm interested in the Miras plot. So we can know about the Miras variable is very long periodic in his processing process.
Okay.
So yep. So for example, in the figure one.
Figure one already. We're at figure one. Miras. Here we go.
Okay. Just like you can see that almost around the 10 years or 50 years is very long-term time scale.
Yeah.
And each the processing about the 100 days to the almost maybe 10,000 days. While the 1,000 days. So we check the line curve. We can see the left-hand side, the regular Mira we see, they have a more stable than the non-regular Mira. So we can see the non-regular Mira have a large long-term trend or long-term variation in his line curve change. Yeah, so we want to use the technology to divide these two parts of the Miras. So we use the random forest algorithm. So yep, we can see the figure two. That is one of our design tree.
Wow.
So we have a 5,000 design tree in our random forest. So each design tree you can see they have a different layer and different leaf to decide which Mira is the regular or non-regular. So it will get more design, divide this classified to non-regular and regular. And he combined the 5,000 design tree to do the major vote to vote that is a regular or non-regular. Yep. So we can move on to the figure three.
Okay, got it. We're going to use an ML, and here we go. There we go.
Yeah, thank you.
You're welcome.
Yeah, just like I mentioned, we use the random forest, so we need to use the feature. We use the feature to let the technology to know how can it use inside the design tree. So we use the feature analysis of the time series. That is the Python package. So we use this package, we can get the 12 feature about the line curve. So we use this 12 feature input to our render forest. So that can do the classify. So we can check the figure 4. So that is the ROC curve. So we can see the area is 0.94. If the area is equal to 1, that is the perfect classifier. So in our technology, in our Python package, that is a very, very good the classifier.
Yep. Okay, remind me what an ROC is. What's an ROC?
Oh, the ROC.
What does ROC mean?
Just hold on.
Yeah, okay. Somewhere I'm looking at, okay, I don't know what an ROC is. Let's find out what an ROC is. We shall find it.
Maybe down below with session 2.
Yeah, because now we're in the decision trees. I didn't see anything there. RFs. Those are the inputs. That's scikit. RF must be down. Receiver operating characteristic.
Yeah.
Got it. Got it. Receiver operating characteristic curve. Okay, I'm with you. Thank you.
Yeah, the ROC curve can tell how good is your classifier.
Yes. Okay.
Yeah. So we can move on to the figure 5. So we choose the 30. We choose the 30% training data to do the testing. So we use the testing data to input to our render forest. So we can see the true regular can be defined. The regular is about the 91%, and non-regular to define to the non-regular is 94.5%. So each of them are more than 90%. So that is very, very good. Not very, very good. That is good to use to the classifier. Yep. So yeah, so we input so we choose the 100 regular Mira and 115 100 non-regular Mira to do our training data. And use this training data, and we collect the whole LNC and SNC, the Mira, to do the feature and input to our machine. And we divide the whole about the 700 the regular Mira and 1,300 about the non-regular Mira. Okay. So we can move on.
We did our good classifications. There we go.
There so okay. So when we classify to the regular Mira, so we analyze with the regular Mira part. So we can see the light curve about the regular Mira. We can see the regular Mira's light curve, the maximum time. The maximum light time is very stable. It's very stable. But the minimum time is have some fluctuation or some curve or some huge long-term trend. So if we do with the prioritization, we use the min magnitude, but the min magnitude we do the prioritization. So the magnitude will be caused by the stable maximum light and the unstable minimum light. So we use the maximum light compared to the mean magnitude, the mean magnitude, magnitude
Okay, I'm with you.
to do the purification. So
Yes.
we can see the below the figure 7.
I'm sorry.
Yeah. So we can see the left-hand side, the coverage or Austin ridge, the mean magnitude sigma. O is greater than the maximum light sigma. But
Yes. Okay.
yep.
Okay.
Yeah, but the minimal light,
Mm-hmm.
the sigma is a correlation with the mean sigma light. So the mean magnitude will be caused by the minimal light. It has some some effect of that.
Okay.
Yeah.
Oh.
Okay. So we can. So this part will be more than the mean magnitude. In the pure reaction, they have a large scale.
Okay.
Yeah. So we can move on, keep on in the pure reaction.
Yes.
Yeah, that's
yes.
Yeah, this is one pure reaction. So we can see with here we use the two-slope model to fit the pure reaction.
Yes.
So in the coverage and other ridge. So we can see the coverage in the purification is the more get the huge slope.
Yeah. Okay.
The coverage, but in other ridge is more smoothly. But in coverage we can see the mean magnitude. The red point will huge scaled in other ridge. And by the maximum light, the scale is more smaller in the purification distribution. And the old data is also have that kind of the effect.
More data though, it looks like there's more oxygen data points than carbon, yeah?
Yeah, it's more than oxygen.
Okay.
Yeah, so we can keep going. The next,
are some of the parameters of the models.
Yeah, we have the second models. We have the two-slope model and the quadratic models. This is two parts. So we feed the oxygen and carbon and O of them, and we also input the SNC to the compare with the maximum light to the mean light in the pure reaction. So how our result can show the maximum light will be greater than mean light in the pure reaction fitting. Yeah. So
yes.
Yeah. So this is the next three picture is about the quadratic model and the whole data with the LNC and NCC.
I see. Okay, right. So we had it for the two different models. I'm with you. Yes.
Yeah, that's a part of that.
Oh yeah.
And yeah, so yeah, it's a great. This is our major result. One of them, our major result in this study, and we can keep on to the down.
I admire
Yeah, we can go to the non-regular Mira.
Okay.
Okay.
So the regulars look good. All right.
Yeah. So
here we go.
Yeah. Now we go through the non-regular Mira. We can see that just like before I comment, the nonregular Mira have a long-term trend in their light curve. So we assume the long-term trend maybe has some periodic, maybe. So within our math, we fitting with the light curve with the short-term pulsating part and the long-term part.
Okay.
And this long-term part have some periodic changes. So we have the three parts. And use these three parts, we can get the short-term periodic and long-term periodic. So we compare the ratio of these two periodic, so we can see.
Okay.
The most ratio is in the about 5.
Okay.
Yeah, it's about 5. And also, we found the coverage, the number of the coverage is more and more greater in average than average in the non-regular Mira.
Yes.
Yeah. So yeah, we can go on.
Okay.
And
Here's our short and long ones. Here we go.
Yeah. So just like this one, so we can see the dashed line. That is a long-term trend.
Right.
The dashed line is a long-term trend, and the combined light curve is the solid line. So we figure these two parts to figure out the light curve. Yeah. So yeah, we can keep one.
Very good. Very good. I'm with you. Okay.
So
15 PLs.
Yeah. Okay. Yeah. Also, we want to know this non-regular have some period relation or not.
Yes.
So we try to do the period relation with this part. And also we try to do the long-term part. The long-term periodic maybe is correlation with his magnitude, but in our result is not correlation, is very close. And the ratio compared to the magnitude is also the case.
Yes.
So
okay.
Yeah. So we think the long-term map maybe not, it may be not correlation with the pulsating part. So I will remove the long-term part.
Okay.
We remove the long-term part to redo the some light curve just like the below. The figure fitting.
Printed almost.
So we remove the long-term part. It will.
Okay. I'm with you. Yes.
Yeah. We remove the long-term part. It will. You can see this is similar to the regular Mira. It's get to the stable. Not having the long-term.
Okay. So now they look regular.
Yeah, it's regular now. So we try to use this part to also to do with the maximum light and the mean light. So we do just the same with similar with our regular Mira. So we can get the figure 16.
Figure 16. Okay. PLs, that max light.
Yep.
Mean light. Yep. Okay.
Yep. So we can see the asymptotic ridge when we remove the long-term part. The asymptotic ridge, when asymptotic ridge will move on to our fitting before our fitting starting. So this will be when this is about the 18. So when we remove the long-term trade, it go to the 14. It's more close to the purification. No matter the maximum light in other region, it can be used in remove the long-term part to do the purification. But the carbon rich is not so good in
not good. Yeah.
Yeah, it's not so good.
Right. Not as good. Yeah.
This part. So
okay.
So we want to know how it's caused by this dumper part. So we collide the SED.
Okay.
So we collide the SED. So we're fitting with the SED with the regular Mira and the non-regular Mira.
Okay.
So we can see that is different in the figure 17.
Yes. So we're gonna take these SEDs. There we go. Okay.
Yeah, we can see this two.
Ooh,
the left hand side.
Yeah.
The left hand side is a regular Miras, but the right hand side is a non-regular Miras.
Okay.
So we can see the SED presents a very different in their peak position.
Yes.
So
yes.
We try to model of them. So we use the just like the two disc model. We have the inside we have the star part, and outside we have the dust shield outside.
Okay.
So our thing, the radiation will come from these two parts. So we fit with these two parts. We can see the red line is about the star part, and the blue line is the dust part.
Okay. Yep. Yes.
So we can see there's a different peak, and also we want to find or already have the model to fit the SED. So also try to with the dusty is used in the SED fitting, the package.
Okay.
Is very useful.
Yeah.
And so we can see the arsenal ridge. Yep. So yep, it's also the 17.
Oh, 17. Sorry.
Yeah, I'm not finished.
My bad.
So we can see the left hand side, the regular Mira, you can see the dusty, the black dash line. That's from the dusty. We can see that have a sun radiation line in the mid infrared.
Okay.
Yeah, but in our CD, this part will not fitting so well. But in the star part is very good.
Yeah.
But we also try to with the non-regular, but it's not so much model can fitting with the non-regular Mira. So we just use our own model. Okay.
Okay.
So yeah. Now we can move on.
Okay. Okay. Good.
So we can move on to the.
I'm with you.
The 17.
Deposits. Okay.
So
good.
compared to these two figures, so we can see the peak with the regular Mira is almost about the 10 micron meter.
Okay.
And but the non-regular, the peak is from the 10 micron or to the mid infrared.
Yeah.
So they have a more and more dusting part in the non-regular.
Okay. Oh yeah. Okay. Yep.
So we also collect the JHK band to do the color diagram. So okay.
18. Yes.
Yeah. So in this part, we can see the blueprint. That is the dusting thick. That's the thing. It's the less the dusting Mira.
Okay.
And the green point is the dust reaching Mira.
Dust rich. Yes.
So
all right.
We do to compare our regular and non-regular. So we can see the regular Mira will be more left-hand side on down left-hand side the part of the regular.
Yeah.
And the non-regular is right up top in this part. So we think that is a dusting. In the non-regular is the
Okay.
less dusting in the
Yeah.
regular Mira.
Uh-huh. That's a good point.
Okay. So in SED and color diagram, all present the non-regular has the dusting. It's very, very dusty.
I got it.
Okay, so we can keep more on to the 12 NG.
Very good. 20, we got some light band curves.
Yeah, so we also tried the time series, the color change.
Okay.
The color change with the time series. You can see the left hand side, that's the example of the regular Miras.
Okay.
When go up, the color will be go to the blue, just like the normal prosthetic model. When the make you to go up, the radius will be go down. The temperature will go up, and the color will be go to blue. That is normal prosthetic process. But in the right hand side, the non-regular process, we can see the whole light curve. When the whole light curve change, not the prosthetic change, the whole light curve change.
Yeah.
The whole light curve change when the maximum light time with the whole light change. It will be go to the just go to the color will be go to the right, so the color will be red.
Yes.
In the maximum light.
Yes.
And the whole light go down. The minimum light time, the color will go to the blue.
Okay.
Yep. So we find a lot of the study to find they have some similar part of them. So we found to something similar situation with this part. It's just called the blue effect in the young solar object.
Okay.
So it's just like when the whole light go down, the dusting will get more and more extinction and more is the scattering.
Yes. Yes.
So when the dust is scattering, all the red light scattering, so the color will become the blue. Yep. So that is
very good.
Yeah, that is we can find the similar situation in this part.
Cool.
And we also to do the CND, the color magnitude diagram, just below.
There you go.
So we can see the regular part is always on above of the 17 magnitude.
Yes.
But the non-regular can down to the 22. And also we can see the slope have the change to the this part is go down, go up is the red, the blue, then is the red, but in the minimum light we go to the blue again.
True. Okay.
Yeah. So in the CND, it also the different in the regular and non-regular.
Yes.
Okay. So we can keep moving on to the 22.
22.
Yeah. So
P radius.
So when we fitting with the SED, we can get the radius of the star.
Yep.
So in the fundamental model with the Mira, they have the line your radiation versus your periodic. We will below to the dash line, just the dash line in this figure, right hand side. This line is called the dash line.
Yes.
And
yes.
Each fundamental Mira should be below to the this line. So we in our regular Mira in our SED feeding, we can see the whole regular Mira is below to this line. It's compared, it is very easier. It's compared to another study, is very consistent. But in the
okay.
Yeah, but in the non-regular, the 22, it is not 23. The non-regular Mira, it didn't follow this rule because they have a large dust part. It will absorption or it's scatter or something. It cover is a huge shield cover the star. So we cannot directly see this star. So it will maybe cause this cannot follow this rule.
Okay.
Okay.
I'm waiting.
Yep. And we also try to find the dust shield, the radius is consistent or not consistent with the periodic, but its precisely is occurs. It's not relation with the periodic and the dust, the middle one. And also we think the long-term periodic maybe have the correlation, but the result is not show up. It is also no relationship in the long-term periodic and the dust
short
radius.
Got it.
Yep.
Very
so
cool. Very cool.
Yeah, so we use the machine learning technology to define these two parts just for the light curve and find to his the difference between these two stars. But it's just for the light curve classify, not so generally physically the classify. It's just for like of the classifier. Yep. So
very nice.
Yeah, we see but use the machine learning can easily define these two parts.
Right.
So the machine learning is very, very useful tools to define anything. To divide anything. So that is very good. Very good technology. And yeah, so
absolutely. That was funny. Very good. Very good.
Okay.
Jia-Yu, I want to thank you so much for walking us through your very lovely AJ article. Thank you.
Yeah, thank you.
All right. So you kind of hinted at it a little bit as you walked us through your paper. But where do we go over the next 2 to 5 years, let's say? Are there additional surveys going on right now on these? Are they being looked at maybe in other wavelengths? Is there theoretical work that could be done? Just kind of where do we go over the next 2 to 5 years?
Finish the PhD degree.
Well, yes.
Yeah.
Yes.
Yeah, and maybe just keep follow with maybe the more archive data or more survey.
Okay.
Or extend to the local glassy, the Mira, or to maybe the glass plane or glassy bulge. It has in our local glass, it's a huge database with variable star.
Sure.
So maybe could keep go on in this 3 or 5 years inside.
After your PhD. After your PhD.
Yep.
Yep. So when do you graduate?
I'm not sure, but maybe I think this winter or next summer.
Oh, very good. Very good. Well, I look forward to calling you Dr. Wu. That'll be great.
I think so. That
would be wonderful. I look forward to doing it.
Yeah, that's wonderful.
Yeah.
I really hope so.
This is fantastic. Jia-Yu, thank you so much. And that'll do on this one, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Bye.